So our next researcher is Valery Milner.
Hello, everybody. My name is Valery Milner, and my group works at the intersection of laser physics, molecular science, and quantum condensed matter physics. Let's start with laser physics. We use a very unique laser tool known as optical centrifuge. There are currently 3 operational centrifuges in the world, and 2 of those optical centrifuges are in my research lab here at UBC. A centrifuge is a pulse of a high-power, ultra-fast laser whose polarization vector rotates faster and faster as you move along the pulse. This is shown schematically with the brown corkscrew shape at the upper left corner. So now moving to the molecular science, what happens, we ask, to a molecule when it interacts with such a pulse, a centrifuge pulse? It turns out it's forced to line up with the polarization vector and follow its accelerated rotation. And in the process, the molecule spins up to some extremely fast rotational frequencies of order of 10 terahertz, or equivalent to some 100,000 Kelvin on the energy scale. So it enters this exotic molecular state known as a molecular super-rotor. What's important is that we have full control over molecular rotation, its frequency and its direction. So we have studied this molecular super-rotors for quite a few years and discovered tons of unusual properties. An example is shown in the lower left corner, which illustrates that by controlling the rotation of a molecule, one can actually control its magnetic moment. And as a result, a gas of molecular super-rotors becomes magnetized. Similarly, you can control optical properties, refractive index, acoustic properties, etc., with laser light. But now we're entering an exciting period in our research. We use super-rotors to probe and understand complex quantum systems beyond gas phase. 2 examples are shown here. First, we create an ultra-cold plasma of molecular super-rotors. That's the middle example. Here, the rotating objects are ions, and they rotate in the soup of free electrons, and they interact obviously via Coulomb force. And because of that interaction, we expect very, very interesting plasma dynamics, such as collective rotation. Second, we implant molecules inside superfluid helium and spin them with this optical centrifuge, which is illustrated at the bottom right corner. Superfluidity implies no friction to a certain critical velocity, and the question is, how exactly does it break down on an atomic scale? So optical centrifuge is one of those ideal tools, and probably the only tool that allows to scan the velocity of a microscopic defect, in this case, a rotating molecule. 70 years ago, superfluidity was actually tested with a mechanical rotation of a macroscopic spinning top. And now we have an absolutely unique opportunity to zoom in and see how it works at the nanoscale. Thank you.